Welcome to lesson 3.3a on Newton's second law. This one, in case you haven't guessed, is all about force. So, defining an inertial is essentially the mass determined by a known force and acceleration. Now, Newton's second law basically says that the acceleration of an object is proportional to the force acting upon it and inversely proportional to its mass, essentially summarized by the formula F is equal to ma. But it is expressed on the formula sheet this way. A is equal to F over m, which means the acceleration is proportional to the force and inversely proportional to its mass. Now, it is important to note here that the overall acceleration of the object, that this is talking about the net force, meaning we've added all the forces together. This dude standing on the ground, even though he has a force of gravity, he's got an acceleration of 0 because he's got a force holding him up, caused by the floor. And we'll get into that a little bit later, but the idea here is that the net force is 0, and therefore the acceleration is 0, even though there's forces acting on him. And that's what we mean by net force. So let's take a look at this question here. We've got a 22 kilogram object that is accelerating uniformly from rest to a velocity of 2.5 meters per second west in 8.5 seconds. We want to know what the net force is acting upon the object. Well, in this case, we are looking at F is equal to ma, and really we want to find the acceleration of the object in order to find that force. So in order to find that acceleration, we know that A is equal to delta V over t. That change in velocity is 2.5 meters per second over a time of 8.7 seconds. And so we find that acceleration to be 0.287 meters per second squared. Now that we have the acceleration and the mass, we can plug that in here with the mass of 22, the acceleration of 0.287, and you wind up with a force of 6.3 newtons. And force is a vector quantity, and so we have to include the direction. The acceleration was west, and so the force must be also west. Okay, concept checked. What would happen to the acceleration if both the mass and the force were decreased by a factor of 4? Well, A is equal to F over m. Now, if this were divided by 4 and this were divided by 4, notice we've essentially made no change to this object, and so we're going to say no change. What if the mass and the force both increase by a factor of 4? Well, again, A is equal to F over m, and if you multiply it by 4 and multiply it by 4, well, that again is no change. What if the mass increases by a factor of 4 and the force decreases by a factor of 4? So A is equal to the force decreases by 4, factor 4, and mass increases by 4. Well, that would get you a 1/16 of the acceleration. It would go down to 1/16 of its original amount. Well, what happens if the decreases by a factor of 4 and the net force is 0? Well, if this is equal to 0, it doesn't matter what this is. Assuming it's not 0, there's going to be no acceleration on the object. No acceleration. Meaning a constant velocity or uniform motion. right? So, because A is equal to F over m, as we apply a force with mass, we get an acceleration. If we use more force, you're going to get more acceleration. But if you use the same amount of force with more mass, you're going to see less acceleration, meaning a slower change in velocity. So a 3 kilogram blank is pulled upwards with a force of 42 newtons. What's the acceleration of the blank? Well, we could pick any object here, but let's just say a ball. And so what is the acceleration of the ball? You can really fill in whatever you want here, but you've got a force, you've got this, but it's pulled upwards with a force of 42 newtons. Right? So you've got a force upwards, 42 newtons. Downwards, what sort of force do we have? Well, that force is also equal to ma, 3 times negative 9.81. So 3 times 9.81 is negative 29.43 newtons. So the net force is 42 up and 29.43 down. That gets you a net force of negative 12.57 newtons. And because we have the mass of the ball, we can find that acceleration. A is equal to F over m. That acceleration being 12.57 divided by 3 gets you an acceleration of 4.19 meters per second squared. And the direction is up because, again, acceleration and force are both vectors. And negative there, that should be up. A blank colored box. Well, we're writing in red here, so let's just call it a red colored box. The color doesn't really matter. Has a mass of 42 kilograms and pulled along a horizontal surface by a rope that makes a 32-degree angle with the horizontal. If the force to direction is 50 newtons and the tension of the rope is 85 newtons, what's the acceleration of the object? Okay, well, this is 45 kilograms. And we know that this has a tension at a 32 degrees with 85.0 newtons. We also know it has a force of friction of 50.0 newtons. We should put 0.0 degrees. Let's keep everything to 3 digits. Nice red box here. So we can find the two forces here because we know it's not leaping off the surface or falling into the surface. It's moving along, so we really just need to worry about what's happening in that horizontal direction. And so to find this side here, that's 85 cos 32. And that gets you 72.1 newtons going forward. So the net force, 72 one way and 50 the other, is going to get you a 22.1 Newton force. And we don't know what direction it is, but we know that it's definitely accelerating faster. We know the mass is 45.0 kilograms, and so we can find that acceleration being force divided by mass, which is 22.1 divided by 45.0, which gets you 0.491 meters per second squared, in whichever direction it's being pulled. Okay, pause the video at this point, give these two a try, and then unpause the video and see how you do. Okay, so this object, first of all, we need to find the acceleration. We know the displacement, the time, the velocity, so we're looking for acceleration. D is equal to VIT plus 1 FAT squared. You find the acceleration to be 1.833 meters per second squared. multiplied by the mass gets you 1,980 meters newtons. And the direction is going to be that 17 degrees south of west. So we started at rest, a velocity of 0, and wind up moving 17 degrees south of west, right? Which means that the friction which opposes the motion is coming along here, which is going to be 17 degrees north of east. 17, not 70, 17. 17 degrees north of east is going to be direction of any resistance to that motion, because it's moving in this direction means it needs to be opposed in the complete opposite direction. Okay, student stands on a bathroom scale on an elevator, accelerating upwards at a rate of 1 meter per second. What is the reading on the scale in newtons? Now we're assuming that the scale reading is the upwards force acting upon the scale. Okay, that this scale, this dude that's standing on here, has a force up and a force down. And the reading is this. This is really what we are looking for. Well, given the fact that we know that the acceleration due to gravity, ma, this is going to be the 70 kilogram student times negative 9.81. So that's going to be 70 times 9.81. That gets you negative 686.7 newtons. Right? Force downwards. Overall, the net force, we know that this is a 70 kilogram student going up 1.00 meters per second. So overall, that's a 70 newtons positive. Well, that comes from the up and the down combined together. So we could also say that this net force is equal to the force up plus the force down. So that plus 70 is equal to the force up, which is what we're looking for, plus negative 686.7 newtons, which ultimately means that this force up has to be 70 more than the force down, which means 756.7 newtons is equal to the force up. And that becomes the reading on the scale. Okay, a little bit of a trick question. What's the reading on the scale in pounds in question 3? Now, really it's question 4. Apologize for the typo. Question 4 in there. So it's 756.7 newtons. Which would show in kilograms 77.135 kilograms. It's going to show heavier than what that mass of that person actually is. Right? And we're just worried about the reading, not what the actual mass is. And so we're going to multiply that by 2.205 pounds per 1 kilogram. Which means it's going to show 170 pounds. Even though in actuality, they're only about 154 pounds. Try this question, pause the video, and let's see how you do. Now in this question, I'm going to have to fix this. It has an initial velocity of 0, but we'll say that's assumed here. And because of that, we're looking for the final velocity. We can find the acceleration knowing the force and the mass of an electron, and that can be found on your formula sheet. So you have an acceleration of, and that's looking a little bit messy, 5.27 times 10 to the 13 meters per second squared. Right? Massive change in there, but it's only has this force acting on for a very short amount of time because this electron is taking off. With only that amount of contact time with this force acting upon it, it's going from 0 to 5.27 times 10 to the 5 meters per second, or 527,000 meters per second. That's fast. I do hope this helped. If you do have any questions, let me know, and thanks for watching.